Hello, in this video, I will talk about our recent work where we investigate generative modeling through the lens of imitation learning. The title of this work is Maximum Entropy Inverse Reinforcement Learning of Diffusion Models with Energy-Based Models. And this was selected as an oral presentation at NeurIPS 2024. My name is Sangwoong, and I'm a postdoc at Korea Institute for Advanced Study. The main idea we want to disseminate through this work is that generative modeling can be seen as an instance of imitation learning. In generative modeling, we train a model that generates samples resembling the training data. This process is a form of imitation learning, where the training data is expert demonstration, each generated sample is an action, and the generative model is a student policy. This one-to-one correspondence between the two lets us import techniques developed for imitation learning to solve problems in generative modeling. In this work, we tackle two challenges in generative modeling. The first challenge is to train a diffusion models with smaller number of time steps. If we decrease the number of time steps in a diffusion model, the samples can be generated faster, but the sample quality usually becomes worse. Another challenge we aim to address is training an energy-based model without MCMC. The standard training of an EBM requires MCMC because of the intractable normalization constant. This process is computationally expensive and highly sensitive to hyperparameters. In this work, we show that incorporating the idea of imitation learning, especially maximum entropy inverse reinforcement learning, can address these two challenges simultaneously. This paper has two algorithmic contributions. First, we propose diffusion by maximum entropy inverse RL, or D by me, which is a joint training algorithm for a diffusion model and an EBM. Second, we propose diffusion by dynamic programming, or D by DP, a value-based RL algorithm for diffusion models. D by DP serves as a subroutine of D by me. Let's start with a diffusion model. A diffusion model, pi of x, generates a sample through iteratively drifting and diffusing a randomly initialized particle. This process is essentially a sequential decision-making problem where the diffusion model can be considered as a stochastic policy. In conventional diffusion modeling, this policy is trained by a noise prediction loss or score matching. The standard diffusion model training can be understood as behavior cloning in imitation learning. Behavior cloning is a popular imitation learning algorithm where we train an agent to mimic the expert action at each state. In a diffusion model, the diffusion trajectory, which is created by gradually introducing noise to data, serves as the expert demonstration. And the policy is trained to follow this diffusion trajectory as closely as possible. This trajectory provides a more fine-grained learning signal to the policy, which I believe is one of the key factors behind the success of diffusion models. However, behavior cloning is also responsible for the failure model of diffusion models. Let's say we have a diffusion model trained to follow the trajectory of 1,000 steps. If we decrease the number of time steps to 4 for faster generation, the sample quality will deteriorate significantly. This phenomenon can be explained by the well-known fact that behavior clone policies are usually fragile under distribution shift. When the number of time steps is changed, the student policy starts to deviate from the demonstration, and error will start to accumulate so that the sample ends up somewhere very far away from the training data. How can we remedy this problem? In this paper, we propose an inverse reinforcement learning approach for fine-tuning the short diffusion models. Inverse reinforcement learning is another imitation learning algorithm, which first estimates the reward or the goal of the expert from the demonstration data, and then use this estimated goal distribution to optimize the policy. In this way, we can directly train a short-run diffusion model to generate high-quality samples under a small number of time steps. Let's get into more details. In generative modeling, the goals are the training data, and the data distribution P of X is the distribution of the goals. Therefore, we consider minimize the KL divergence between the diffusion model and the data distribution. This minimization problem is essentially a maximum entropy reinforcement learning, where the log P works as the reward. However, in many cases, we don't know the true value of log P, so we have to estimate this from training data. Since we are interested in log P, the energy-based model is a natural choice as a surrogate reward model. We can feed an EBM to data by maximum likelihood, which minimizes the KL divergence between the data P and the EBM Q. Once the EBM is trained, the diffusion model pi can be optimized using log Q as the reward. This pipeline is an instance of maximum entropy inverse RL, as there is the maximum entropy regularization for the policy. While this process is feasible in principle, a naive implementation of this will be highly inefficient due to the normalization constant of EBM, which requires MCMC. Instead, we introduce a new minimax objective function called generalized contrastive divergence. This objective contains the difference between the two previously discussed divergences. Here, the normalization constant is cancelled out, and there is no need to perform MCMC. This minimax problem has a unique equilibrium where all three distributions are the same. We can also show that GCD is equivalent to previously known objectives such as variation of maximum likelihood and adversarial EBM. So using generalized contrastive divergence as the objective function, we propose a joint training framework called diffusion by maximum entropy inverse RL, or D by me. Here, the diffusion model is trained using the EBM as a reward, and the EBM is trained in a contrastive manner where the energies of the training data are decreased, and while the energies of diffusion model samples are increased. In practice, the minimax problem can be solved by alternating gradient descent and ascent. So for each mini batch of training data and generate data, we update energy-based model, and then we update the diffusion model. We repeat this process until convergence. However, the policy learning step for a diffusion model is not trivial to implement. The first difficulty is that we cannot analytically evaluate the marginal entropy for a short-run diffusion model. The second difficulty is that the gradient has to be propagated through time to train a diffusion model. This backpropagation through time usually requires significant amount of memory. Even with sufficient memory, there might be gradient explosion or vanishing problems. To circumvent these problems, we present a novel RL algorithm for diffusion model called diffusion by dynamic programming, D by DP. First, we avoid the marginal entropy estimation by minimizing an upper bound of the KL divergence instead. Second, we remove the need for backpropagation by introducing value functions. To obtain the upper bound, we apply data processing inequality. Data processing inequality states that if we add new random variables, the KL divergence will never decrease. Here, we add the intermediate steps of a diffusion model as new random variables. And this KL divergence becomes the KL divergence between the whole trajectories. When doing this, we need to introduce a new distribution, Q tilde. Since this inequality holds regardless of the choice of the Q tilde, we will simply set this Q tilde as Gaussians. Now we will tackle this upper bound instead of the original KL averages. When we expand this upper bound, we get an expression that is exactly an optimal control problem. Here, the energy is the terminal cost, and the other terms work as the running cost. Tau is a temperature parameter, which governs the balance between the terminal cost and the running cost. Since this is in the form of a classical optimal control problem, we can solve it using dynamic programming and value functions. The value function is defined as the expected future return at a certain state. This expression is identical to the objective function in the previous slide, except that the summation starts from the time t. We will parameterize the value function using a neural network, which may potentially share some components with the EBM. With the value function defined, we can solve this optimal control problem with a standard value iteration. We first train the value function using temporal difference learning. Then we optimize our diffusion model to minimize the value function. These two steps will be performed alternatingly until convergence. So d by me can be summarized by this illustration. So instead of backpropagating through time, we use the value function to propagate the learning signal to the earlier steps of diffusion model. And d by dp serves as a subroutine of d by me. The main application scenario we focused on is the fine-tuning of a diffusion model for a smaller number of time steps. Given a diffusion model pre-trained on t equals 1000, we set t to 10 and then run generations. The samples we get from such a model are highly blurry. If we fine-tune this model using d by me, then we can significantly improve the sample quality. We also get, this can be also confirmed by quantitative results. So quantitative results in CFAR10 are highly competitive. The FID score is even comparable to the full-length diffusion models, even when the number of time steps are set as small as 4 or 10. Also in ImageNet64, D by me was able to achieve quite competitive results. Overall, D by me shows a favorable trade-off between the number of time steps and the image quality. I also want to highlight that the maximum entropy regularization is what differentiates D by me from GAN. And this entropy regularization plays a crucial role in learning the energy function in D by me. In this 2D example, when the temperature is set to an appropriate value, D by me can learn an accurate energy function as well as a high-quality diffusion sampler. However, without entropy regularization, the energy function does not converge to the true energy of the data. Since the energy function captures the training data distribution, it can be used for anomaly detection. We apply D by me to an industrial anomaly detection task and obtain strong results. I am well aware that there are a lot of interest in turning a diffusion model into a single-step generator. Unfortunately, I have to say that our approach is not applicable to a single-step generation because there is no value function can be defined in the single-step generation scenario. However, I believe that there may be potential benefits of multi-step generation which have not yet been fully explored. To conclude, I would like to share a few personal reflections. First, I have realized that many ML problems can be viewed through the lens of imitation learning because eventually we want our algorithm to mimic a certain behavior. Similarly, many ML problems can be framed as sequential decision-making problems because many ML problems involve multiple steps of computations. By this point in the talk, I hope I have convinced you of these connections by presenting D by me and D by dp as examples. I believe there is still much to explore in this direction, and I'm excited to see what the future holds. For more details, please check out our paper. Feel free to reach out to me if you're interested in discussion or collaboration. Thanks for listening.